Now we present the project Computational Tools 1 Design and Simulation of Centrifugal Pump by Group 5. The general index based on context, objective, literature review, methodology, CAT, mesh independence, results, comparison, and conclusion. About the context, we need to know that centrifugal pumps are very important in different industries as food and pharmaceutics. For the reason, it's important to model and analyze the behavior of this machine under different operation conditions. At the same time, we need to know that the pumps are divided by different parts like voluta, impeller, and others that we present in this picture. The principal purpose is design and simulate a centrifugal pump that present a geometry proposed and respond to a specification given by the problem. To achieve this, we need to involve four aspects. First, identify the physical model. Second, using different tools like Excel, AutoCAD, and other. Third, simulate this model to create our pump. And finally, have results and make a comparison with the manufactured pump. Literature review presents four important points in this project. First, CFD, work with numerical simulation to present the fluid mechanisms. Second, the viscosity of the fluid affect the performance of the pump in terms of efficiency, value of head, and power. Third, cavitation phenomenon present where are bubbles in the machine because the pressure is lower than the pressure of the liquids. This have effect in the efficiency. Finally, the Reynolds number present the behavior of the fluid. In this project, we use water and oil in a turbulence behavior. Now we present the methodology. In this slide, we present the specific measure that we need to have in our pump and the properties of our fluids like density, viscosity, and temperature of oil and water.
These are the specifications for the mesh designs. We have a Prince layer measure, a state steady model, and finally a reference pressure of Bogota. Following the design of our pump, we have the next parameters. For water and oil, we have that the impeller is composed by the inlet and outlet diameter, the inlet and outlet blade width, the inlet and outlet blade angle, and the number of blades. And for the pump, we have the nominal head, the nominal flow rate, and the specific speed.
The CAD presents the geometry pump of three parts, impeller, volute, and assembly, with different planes that present a specific measure of our pump. For example, the diameter of impeller, the height of the hot, and other specific measures that we need to know to create our pump.
In order to decide what mesh we're going to use, we make an study of a pump mesh independence. In this study, we compare the number of cells, the processing time, and the mean square error for total head and efficiency in the web. We could find that the reference mesh has a great time of processing that was 0.8 hours and an error of 2.3% and 3% for total head and efficiency correspondingly. So that is why we prefer to use this mesh to make the other simulations. After we decide what was the best mesh, we keep using the program Star CCM and we found the next results. We can see the mesh in the cold water, in the diffuser, in the impeller, and finally in the inlet that is the same of the outlet.
Besides, we present the results and discussion.
The results obtained for the total head of both fluids have slightly differences. For example, in the total head water, we can see that at 350 cubic meters per hour, we have a drop. This could be explained given that in that point the pump initiate to be unstable. However, in the mineral oil, we found that at this flow rate, the pump continues to have a normal behavior, and this could be explained for the differences of density and viscosity. For the results of the efficiency, we make a total of 8 simulations in different flow rates and we make a polynomial adjustment. We could see that in the water there's an inconsistency, and this could be explained for the viscosity of the water and that this liquid is more turbulent than the mineral oil. Besides, the mineral oil have a better adjustment. Also, with this polynomial adjustment, we can find a global maximum, and this is traduced in the BEP. We also make a comparison with the operation curve that proposes the manufacturer with the results obtained of water and mineral oil. We can see that the mineral oil has less efficiency given his viscosity, and the water have certain percentage of error with the theoretical curve. And this is the comparison with the manufacturer in terms of efficiency. We can see that we have a similar behavior. Continuing with the comparison with the manufacturer, we make an R&S analysis. In this analysis, we cross one line above and below the theoretical or the manufacturer line, and we see if our points or the simulation that we made are in this range. So we can say if the results are coherent. As we can see, most of the points are in this range, so this is a good sign. Following the results obtained, we decide to make a velocity magnitude descent. As we can see, as long as flow rate increases, the behavior of our pump is more uniform. And also, always at the walls of the outlet, we can see that the velocity is zero. So we can say with certainty that our simulation has sense. These velocity magnitude descents are for mineral oil, and if we compare with the water, the maximum change of 51 meters per second to 53 meters per second. Also, we can say that as long as flow rate increases, the behavior of our pump is uniform, and also the velocity in the walls is zero. Also, we made a cavitation analysis. In this analysis, we put as a maximum absolute pressure of the pump the vapor pressure of water. If the pump presents this pressure, the pump can cavitate. So we can see that in 4 of our 8 simulation, it can be cavitation. For the mineral oil, we made the same analysis. However, this changed for the maximum pressure, that is 90 pascals. We can see that there's a less cavitation in this fluid, given that his viscosity. We also made an analysis of the wall Y plus in different points of flow rate, and we could see that there's slight changes in the minimum and maximum founded. This means that there's errors in the geometry proposed, especially on the impeller, or this could be also present for the cavitation that has the pump that was explained before. As we explained before, we make a worldwide plus a comparison between different flow rates, and we found that there's slight changes in the minimum and maximum. However, in the mineral oil, we could see that there's these changes are lower than the water present. So this could be also explained that in the mineral oil we present less cavitation than in the water. Finally, we present vector scene when we can see the different velocities and different points of the pump for the water. We have also scenes for mineral oil, and we can compare here that in the water, the point of the blades didn't have that color that represent a major velocity. This could be explained for the viscosity of the mineral oil. The pump has to make more effort in order to propel the fluid, so this is represent for the blades.
Finally, we present the conclusions. We have three conclusions. The first conclusion is that the manufacturer pump is better than the design point because they have a great efficiency and total head. Second, the design point work better with water than with oil in terms of efficient and total head. Finally, the design point has some areas that doesn't present stability.